FastMCP 2 implements the MCP background task protocol through a decorator-based abstraction layer that transforms synchronous function calls into distributed, non-blocking operations. This protocol-native approach enables clients to initiate long-running computations, monitor progress, and retrieve results through standardized MCP interfaces while maintaining execution flexibility. We will examine how a server instance is initialized with a descriptive identifier and how a single tool function is registered with background task capabilities using the task equals true parameter. The code demonstrates the foundational pattern for creating task-enabled components, where an asynchronous function with type annotations becomes a distributed operation without additional boilerplate. Import Asyncio. From FastMCP, import FastMCP. MCP equals FastMCP my server. At MCP, tool task equals true. Async def slow computation duration, int SDR. A long-running operation. For I integer ratioed. Await Asyncio, sleep 1. Return F, completed in duration seconds. This code demonstrates the foundational pattern of creating task-enabled tools in FastMCP. The FastMCP instance is initialized with a server identifier, myServer, which serves as a label for protocol handshakes. The @MCP tool decorator registers the slow computation function as a tool with task equals true, enabling background execution capabilities. This simple configuration transforms an async function into a distributed task that can be executed asynchronously, with progress tracking and result retrieval handled by the MCP protocol. The pattern showcases FastMCP's automatic tool registration system, where the function name becomes the tool name, the docstring serves as the description, and type annotations define the input schema. By using Asyncio, sleep in a loop, the example simulates a long-running operation that benefits from background execution. The trade-off here is between immediate synchronous execution and the overhead of task management, which FastMCP handles transparently through its docket integration. This approach is particularly valuable for operations that would otherwise block client interactions, improving user experience in production systems. Let's break it down. Import Asyncio. Imports Python's built-in Asyncio module for asynchronous I/O operations, event loops, and coroutine handling. From FastMCP, import FastMCP. Imports the FastMCP class from the FastMCP module, which provides the core functionality for implementing Model Context Protocol MCP servers. The imported class will be used to create MCP server instances with customizable identifiers for protocol handshakes. MCP equals FastMCP my server. Creates an instance of the FastMCP class with the server identifier myServer. This instance will be referenced by the variable MCP and will use myServer as its label in MCP protocol handshakes for client identification purposes. At MCP, tool task equals true. Async def slow computation duration, int SDR. A long-running operation. Defines an asynchronous function named slow computation that takes an integer parameter duration and returns a string, decorated with @MCP, tool task equals true to register it as a task-enabled tool in the FastMCP framework. The function is documented as performing a long-running operation, and the decorator configures it for task-based execution within the Model Context Protocol. For I integer ratioed. Await Asyncio, sleep 1. Loops duration times, pausing execution for 1 second on each iteration using Asyncio, sleep 1. This creates a total delay of duration seconds while allowing other async tasks to run during the sleep intervals. Return F, completed in duration seconds. Returns a formatted string indicating task completion with the elapsed time in seconds. The duration variable is interpolated into the F string to create a human-readable completion message. The decorator-based abstraction in FastMCP2 transforms synchronous function calls into distributed, non-blocking operations through the MCP background task protocol. By initializing a server instance with a descriptive identifier like myServer and registering a tool function with task equals true, you create a task-enabled component that can be executed asynchronously. The @MCP tool decorator handles the registration, using the function name as the tool name, the docstring as the description, and type annotations for the input schema. This pattern allows long-running operations, such as the slow computation function, to run in the background without blocking client interactions. The trade-off between immediate synchronous execution and the overhead of task management is handled transparently by FastMCP, improving user experience in production systems.
The decorator whispers to the server, and the task ID escapes before the loop begins counting.